Hi class, we are now on chapter 26.4 and we're going to be looking at the structure of these compounds and isomerization. Now some of you guys are going into organic, so some of the terms that are used here are going to be very, very common in organic, and isomers is one of them. So isomers is something that you should feel comfortable with, because when you get into organic, there's a lot of terms that are thrown at you at once. So the more that you're familiar with some of them, it makes life a lot easier. Okay, so isomers. Isomers are compounds that have the same formula, but they have different structures. So they're attached in a different order. And from there, we're going to break down and look at different isomers. So we have there are different types of isomers. There are structural isomers and there are stereoisomers. And isomers have same formula but different structures. Structural isomers have atoms at different connectivities, so that's where they're attached in different orders. Stereoisomers are atoms that have the same connectivities but different spatial arrangements. How they are spaced out. Remember, you have learned Vesper. You've learned in 111 the geometric shapes of these, and I'll give examples of these spatial arrangements, and the spatial arrangements definitely do affect these molecules, these compounds. So here is so we can see we have the isomers beginning here. Then if we go down to structural isomers, we have different types. We have coordination isomers and we have linkage isomers. And if we go to the other side, so isomers is a term you'll definitely get to know in organic. Another one is stereoisomers. This is a big one too. You will learn about stereoisomers, or this is another term that will definitely be thrown at you. So the sooner you understand isomers and stereoisomers, that's really great. And then we can get to optical isomers, which are also enantiomers. And enantiomers is another word you are definitely going to study. You'll have a lot of studying with enantiomers. So a little bit of organic is kind of spilling into this section. So on stereoisomers, we have the atoms that have connectivities but different spatial arrangements, and those spatial arrangements either end up as geometric isomers, which is cis and trans, or I'll tell you, I don't remember what this one's called. It stands for facial, so I'm going to say it's face and mer. And then we have optical isomers, which are enantiomers. So with structural isomers, the first one, remember, structural isomers are atoms that are connected to each other in different ways. One of them, as we break those down into different groups, is coordination isomers. And those are pretty much the easiest ones to understand out of all these, because coordination isomers simply have to do with the fact that a ligand exchanges places with a counter ion, which is uncoordinated is the term. So it's not attached to the metal, but then it attached, so they switch places in a sense. So what was once in the bracket is now outside of the bracket, and what was outside of the bracket is inside the bracket. So that's what it means where a coordinated ligand exchanges with an uncoordinated counter ion. So as you can see, we have two different cobalt complexes here, one with the counter ion of a bromide, and the other one with a chloride. So then when we deal with linkage, which is the other one, so if we take a step back, coordinations are probably the easiest. They're just ligands that exchange places with counter ions. Very easy. You can visually see that when you look at the compound when it's in its formula. Then we have linkage isomers. So this is from the structural isomers, which is coming from the isomers. Linkage isomers are ligands that coordinate, they coordinate to a metal in different orientations, so in different ways. So if we get down to linkage, so in linkage, here we can look at a thiocyanate group, or a thiocyano group is what it's called here. So we have a sulfur, we have a carbon, and then we have nitrogen here. And it can bond through the metal, either through the sulfur group or through the nitrogen group. And how you know that is based on how it is stated. So we have a palladium complex here. And as you can see here, and they underlined it so you can see which is the donor atom, which means which is the one that is donating an electron pair to the metal. Because remember, these are inside the bracket. So we can see this ligand, it's donated through the sulfur. So that is called a thiocyanato or cyanato linkage. I really don't know exactly which way, but even in chemistry, people say things different. Some people say an amide bond, some people say amide. So even with chemistry, we don't say things right. Who knows which one's right? So this is thiocyanate and linkage. So that means that it's coming from the sulfur bond. By this term, it's telling you it's this bond. But what if it is attached to the nitrogen bond? And that means that it's isothiocyanate. I'm probably not saying it right. I apologize if you look this up and somebody's saying it different than me. So these are linkage isomers, two coordination compounds that share a common ligand that bonds to the metal through different groups. So that means it can, in this case, it can bond through the sulfur or it can bond through the nitrogen because of they can have lone pairs on them, and that's what's being donated to the metal ion. So thiocyanate, isothiocyanate, and that tells you it's nitrogen, and this is sulfur. And these are just one of those fun things that you just have to learn to know which one it is. But if we look here, so we'll look at another linkage isomer, and this page is in your book. How it is coordinated or bonded to the metal atom also affects how it looks. So in this case, we have a yellow kind of orangey complex, and here we have an orangey red complex. And how it is bonded. So here we have, if we look at this cobalt complex, we have we have a NO2 minus ligand, and if it is bonded through the N bond, it's a certain way, and if it's bonded through the O bond, it's another way. So if we look at this one here, we have NO2, and the NO2 ligand bonds to the central metal through the nitrogen. So if it's bonded through the nitrogen, you see it's been bolded out here, so it is nitro. So this yellow complex is pentaamine nitro cobalt 3. And that nitro tells you it's bonded through the nitrogen. But what if it's bonded through one of the oxygens, which also have lone pairs on it to donate? In this case, this is bonded through the oxygen. And because it is, it's now nitrito. So, or nitrito. Again, here we go with saying stuff. Red complex. This is pentaamino nitrato cobalt 3. And that tells you it's bonded through the oxygen and not through the nitrogen. So these little differences of ligands and how they are oriented towards the metal, the names tell you which way it is bonded to it. And again, it's one of those fun things that you're just expected to know. Okay, so ligands capable of linkage, isomerization, and here's a list of them. A couple of them you can see with nitrito. That means it is bonded through the oxygen, a lone pair on the oxygen. When it's nitro, it's bonded through the nitrogen. And then we have over here a cyanate group, and here we have a cyano if it's through the carbon, and if it's through the nitrogen, it's isocyano. And again over here, if it's through the oxygen, it's cyanato, and if it's through the nitrogen, isocyanato. And over here with the sulfur, which we've already covered, thiocyanate, and over here, isothiocyanate. These are those terms you're just expected to know in chemistry. Okay, so now we've covered this side of it. We've covered isomers, structural isomers, coordination isomers, and linkage isomers. Now we're going to go over to stereoisomers, which is different spatial arrangements. And through those, we have cis-trans isomers and we have opticals. Now, if we go back up to the other one here, you can see that through they call it, in this one, cis-trans. This is from another book. But that's actually broken down on this side. If you see, it's geometric isomers, and then there's cis-trans and face-mer. And this is actually from our book. So this is what we're going to cover more than what the other one's saying. And then we have optical isomers. All right. So stereoisomers, which is what we're here looking at, are isomers that have the same atom connectivity, but there's different spatial arrangements. And those spatial arrangements determine if they're cis-trans or optical isomers. So cis-trans, and then they have the face and mer. Those are based on how they are. It's good for, I'm going to show you examples of these. And that refers to the ligands. So when we say cis and trans, we're looking at how the ligands are oriented around the metal center. Excuse me. So with cis means that the same ligands are occupying positions next to each other. So when we're looking at a center, and I have pictures I'll show you, but I want to go through the definitions first. Cis means they are next to each other. They are neighbors. And they are connected to the center atom but they are next to each other. Trans, they are on opposite sides of each other. They are not near each other. One is on one corner and the other one's on another corner. They are completely opposite of each other. So cis is think of like cis is together and trans is apart, is another way to say it. So geometric isomers are that differ in orientation. So a cis trans for a square planar has 4 coordinations, which means it has 4 ligands to it, has a general formula. And how do I know that? Because there's 2 and 2 and we add these together and that's 4. And 4 is either a tetrahedral or it is a square planar. And tetrahedral is not something that we're looking at in this. So here we're looking at square planar. So we have a platinum complex. And the easiest way to have you understand this is look at the green. The green are the chloride ions. Here is a cis. They are directly next to each other. And they are across from the amino groups, which is ammonia. So you can see that they are directly across from that. Now here, if it's trans, they're across from the amines, but the ammonia groups, but they are next to each other. So this is what I mean by neighbors. That's cis. That means and think of it as same side. Trans is opposite of each other. So if you see here, they are 180 degrees from each other. And that's not always the way it will be, but in this one's a good example of 180 degrees, but they are neighbors to the ammonia groups. So that's what trans means. They are far apart and opposite, so different corners, where cis are directly next to each other. So it's easy when you focus on the green ones, you can kind of see this a lot better. It doesn't look as complicated. So in a cis-trans isomer, 2 identical ligands are adjacent to each other. That's called cis. And so you can see, again, look at the green, you can see them together. Now, what would a coordination for this one be? We'll count the ligands, right? We have 1, 2, 3, 4, 5, 6. 6 ligands is a coordination number of 6, which is an octahedral complex. So how do you deal with the octahedral? Well, you would look up what an octahedral looks like, and you can see it's kind of got an X here, like a square, but then it's got 2, one at the top and one at the bottom. So it's an easier way to draw this, because your book's going to want you to draw some of these. I'm not going to expect you to draw them, but you should be able to answer some of the questions. So I'm not going to put anything up about drawing anything on here. I know some of those programs are awful, so I really do try to avoid them. But I still expect you to have an idea of what shape you're looking at and if you needed to draw them. By the way, excuse me, in chemistry, you do nothing but draw molecules like this and everything else under the sun. You will get very good at drawing stuff like this, and they will tell you, draw this, and you're supposed to know how to draw it. A cis trans or a cis something, you're supposed to know how to draw it, and you will get tired of drawing if you like drawing. So how do you draw this? Well, this is like an X. You see it's X, and then there's a top and a bottom. So that should give you an idea. It doesn't matter that this is kind of bulky. If you just focus on the blues, you can see that this is the square, and then you have a top and a bottom. So I'm trying to give you an idea of how to draw these if it's an octahedral. When you deal with the trans, you can see they're directly across from each other. So no matter what, they'll never be directly next to each other like neighbors. And that allows that's what the trans means. So that's what this applies to. Why is there 4? Because there's 1, 2, 3, 4, and then you have 2 of the chlorides. Add those together, that's 6. The coordination 6 is an octahedral. All right, so this is a better way to see what you're dealing with. This is a square planar complex, and the square planar complex got 4 ligands to it. So because it doesn't matter that ammonia is bulky, it's still got 4 ligands based on the coordination number. So if you look here, you can see that the chlorides are together, or the ammonia groups are together. This is a cis, and you would write cis. This is, again, another big thing in organic. You write cis in front, or you write trans. That tells you how to pull out the structure and draw the structure if you needed to. So we would need to know that information. So in this case, this is a cis, which means they are together. And this is, and you wouldn't draw them across from each other. Why? Because these rotate. They're rotating. Let me see if I can do it like clockwise. So if you have these rotating, these are not always going to match up, and they'll end up being trans. You see how these are? Think of these moving in one circle and these moving in another circle here. So they will end up like this most of the time. So we need these to be on one side. So if you split this way, these are on one side, these are on the other. If you split this way, they are as far apart of each other as possible. So this is trans. Geometric isomers, again, we're looking at a face mer. And face stands for facial. And the mer, and I know I'm going to slaughter this name too, stands for meridional. I don't know how to say that. These terms, I'll be honest, when I was a student, I don't remember this face mer. Some of these terms and some of the way that you guys are taught chemistry is a lot different than from when I was taught as a student. I know you guys think it's difficult, but I actually think that they've cleaned up a lot of stuff and made it easier with different terms than when I did it. So these have 3 identical ligands in the octahedral. So basically what I'm saying is you guys should know how to draw an octahedral complex. Maybe not as complicated. Try to visually look at what the blues are and not the things attached, and that makes it easier to see that. These are all hydrogens, you guys know that. Okay, so why? Because 1, 2, 3, 4. There's 4, there's a square, and then you add a top to a bottom. Now, the difference between these is that the facial means that they're all in one face. They're making one face. They're all close to each other in one face. So you see it here. However, if you see this one is not. It's kind of an arc. So where this kind of looks like it's a triangle, this one is going down. You can see kind of like like a half circle. So it's not the same thing. And with this one, the general formula is an Ma3B3. So that's what you're seeing here. There's 1, 2, 3, and 1, 2, 3. And that's going to give this complex compared to something that is an Ma2, which is 2 and 2, or 4 ligands and 2 ligands. 2 of the same and 4 of the same. So these are general complex formulas that you definitely should be comfortable with. So we're still under stereoisomers, but we're looking at optical isomers now. Now, chiral is definitely an organic word, and you're going to get tired of it because you're going to learn a lot about chirality. And chirality has to do with a compound. And when you start getting into organic, you get into bigger and bigger compounds. And you can have a compound that has several chiral centers, and you have to focus on all of them. What is a chiral center? It means you have a center atom, and it has 4 different ligands attached to the center. And because it has 4 different ligands attached, the geometry may not always look, they may look exactly alike, but when you try to lay them one on top of each other, they are not superimposable. And that's what chirality means. So in this, that's what it tells you right here. It can exist in 2 different structures. They look exactly alike, but they are non-superimposable. And that means they're called enantiomers or optical isomers. And I'll tell you right now, I only know them as enantiomers because that's a total organic thing. Optical isomers, it's because they polarize light differently. So when you get into, I don't think any of you guys are going further into chemistry except for a few of you. But there's something called polarimetry that has to do with light. And you can determine the handedness, the left or right handedness of a molecule based on how it polarizes the light, meaning how it rotates the light in an instrument. And based on how it rotates the light and how much it's rotated, you can determine which handedness these molecules are. And that's what this is about. One molecule will rotate light a certain direction and a certain amount, and the other one that looks exactly like it but is non-superimposable on it will rotate the light in the opposite direction by the same amount. So that has to do with your hands. Your hands are mirror images of each other, but if you put one palm down and you put the palm on top of the top of your other hand, they don't line up. No matter how much you try, you'll never get your other thumb to match on the other side with the same face with the palm down unless you cut your hand off. Please don't do that. That's what superimposable, non-superimposable images are. They look alike, completely alike, but you can't stack them on each other and have them stack completely together the right way. Now, most coordination compounds exist as optical isomers, are octahedral, and they contain 2 or more bidentate ligands. Remember what the bidentate ligands mean? Ethyl-diamine is one, it's abbreviated EN. That is one that has 2 teeth, so it's a big ligand, so it can attach on one side of the ligand, and it can attach on the other side of the ligand around the metal ion center. So here is a perfect example. EN means ethyl-diamine. I just said it, and ethyl-diamine. So that's what this is, ethyl-diamine, and because it's really a long name, we abbreviated EN. And that's what wasn't a very good, I don't think this is a very good picture of what it's showing. So I found one online where you can see these are all different. This is a center. This is a chiral center. So there's 4 different atoms attached to it. And in this case, so this is organic right here. This is what you guys are going to draw. If you go into organic, you're going to have to learn how to draw these. I don't know if I went over these with you, but let me explain what this is. This is a carbon center, carbon center. These are the same. Now, if you're looking at this one, the dark wedge, so anything that's just a stick, so you see these 2 are sticks, that's in the plane of your laptop or whatever you're looking at. That's in the plane. That's in the piece of paper. Now, this wedge that's coming out, that's directly towards your face. That's how you're supposed to visually see these. That means that this chlorine is coming directly in your face. And this here with nothing attached is a hydrogen. And it is directly out in the opposite direction in the back. So like a tail. So you have one tail going out in the back. You have this wedge going directly in your face as a chlorine. And the hydroxide and the hydrogen here are in the plane of the paper. So this is a way to try to show you a 3D of what you're looking at. And now if you look at this side, it's the opposite. So you see this one's kind of going this way. This chlorine is still coming out. It still has a tail because they're superimposable and super non-imposable. They look exactly alike. But if you pick this one up and put it on top, they don't match up. And that's the non-superimposable. So I think this picture here looks better than whatever this is trying to show. And I think this is a poor quality of trying to show this here because it's not really doing a good job in my opinion. But these attached, so these ethyl-diamines, that's what it's trying to show you with this, is that this is one compound, these little things attached, that's another compound, to try to show you that those are attached to each other. But I think in this case, something simple will allow you to understand it a little bit better. Okay, so let's do some problems. Classify each of the following compounds such as structural isomers, stereoisomers, or not isomers at all. If they are isomers, then we need to classify them as coordination, linkage, cis-trans, or optical. So I'm going to jump to B because B is the easiest one. Why is B the easiest one? Because it's telling you it's a cis and a trans. So in this case, it's a stereoisomer. So remember what cis-trans is categorized in, and it's stereoisomers. And it's cis-trans. So you can see the cis here, you can see the trans. Super easy. Now, let's go to C. We have a chloride, we have a coordinate ligand bonds of an ethyl-diamine, and we have a chloride, and we have a nitrate in front. We have an ethyl-diamine that matches up, we have a chlorine, and we have a counter ion of hydroxide. These are not isomers. There's nothing going on here because this didn't go in and this didn't go out. These are 2 entirely different things, not at all an isomer. Now over here, if we look, we have a fluorine on the inside of the bracket, and we have a chloride in the front and out of the back bracket. Now inside here we have a chloride and we have the fluorine on the outside. So this is a structural isomer. So in this case you can see that the counter ions went in and one of the counter ions went out. So this would be a coordination isomer. It's not saying it, but that's what this is, a coordination isomer, because the counter ion and the ligand switch places. All right, so these are examples in your book. And this is where it's expecting you to draw. And I'm not expecting you to, I'm telling you right now, I'm not going to ask anything about drawing. You're not going to have to draw anything on any of my stuff because I have found that because of being online, students have a lot of hard, some people just can't get the drawings down on the program, and it's not worth the effort for everybody else when I have like 6 students that are really struggling with this. So, and I mean struggling, it might be their computer programs or how old their computer. There's just a lot of different problems. Not everybody has the same problem, but they have problems with it. So I'm not going to ask you to draw anything, but you should know how to have an idea of how to put this together. This is understanding geometry. Are you looking at ligands that are monodentate, bidentate? I've given you these lists, and this is what's going to help you understand it. So this says to draw the structures. I'm not going to ask you to do that, but you should have an idea, loosely draw it on your own so you can see what you're dealing with. Identify the coordination number and geometry around the metal. Well, that's easy. We have an ethyl-diamine and we have a chlorine. Now, that's not easy. It is easy, but it's not, because if you said this coordination number was 4, you'd be wrong. Why would you be wrong? Because chlorine is a monodentate, but ethylene diamine is a bidentate. And for every one bidentate ligand, it occupies two sites. Remember, it can bind two teeth. So this is 2, so we have 2 of those, and 1 equals 2, so we have 2 plus 2. So one ligand can attach with 2 teeth. Another one of these ligands can attach with 2 teeth. So 2 plus 2 is 4, plus 2 chloride ligands, and that's 6. This is a coordination number of 6. 6 is an octahedral complex, and that's what this is saying here. So now we need to determine if this is a cis-trans. How do you understand that? Because of those general formulas. That's what's going to tell you which one you're dealing with. So in this case, you got to understand that this is actually 4 and not a 2, because each ligand attaches at 2 sites. So you're looking at this one here, which is a cis-trans isomer. So you don't need to technically draw these, but you do need to understand to step 2 how to do this and what you're looking at. Okay, so draw the structures, and here's another one. So let's go through it the same way. So you need to understand if you're looking at something that is monodentate. This is going to be a square planar because we have 4. This actually is a 4 coordination number. This is in D8, and D8 tends to be a square planar. So you're looking at it here. So is it a cis or is it a trans? And so identify if this is a cis-trans or a face-mer isomer, and it can only be a cis-trans. There's nothing, those has to be more of an octahedral complex, which this is not. So this is going to be a cis-trans. You're going to see it as a cis, and you're going to see it as a trans. Okay, recognizing and drawing optical isomers. Determine whether a cis-trans isomer is optically active. So I want you to draw the trans isomer and its mirror image. I'm not going to really ask you to do something this complicated, I'll be honest, but I want to cover this anyways. In this case, you draw one, and you can see, so here's the ethylene diamine, so you can see it's attached in the square planar part of it, and then the chlorides are right here. So you can see it's trans, and they are superimposable. So these can stack right on top of each other because these bidentate ligands are the same. However, so in this case, these are 2 identical. There's no optical activity because in order for them to be enantiomers, they also have to be chiral centers. So they have to have 4 different things attached, and that does not happen here. That's probably as far as I'm going to get into delving into this, because I'm not going to expect you to draw on and look at this and be able to tell if it's an optical isomer. It's not a chiral center. If it's not a chiral center, it's not going to work. All right. So I'm pretty much going to show you, in this case, you can see that this is a cis, and this is not going to work, because see, one of these goes out and one of these goes in, one of these goes out and one of these goes in. I'm going to stop with this because it's kind of confusing to explain it, and they're using big molecules. So again, I'm not going to really ask you that much about optical isomers unless it's what I've already covered, and you really have to have a better understanding of how to draw these. And it's not really that easy being online to show you how to spend time doing this. If we were in class every day, it would be different. Okay, so isomers are compounds that have same chemical formula but different arrangement of atoms. Structural isomers have same chemical formula but different atom connectivities. 2 main classes of structural isomers are coordination isomers and linkage isomers. Stereoisomers differ from structural isomers in that their atom connectivities are the same, but their spatial arrangements, which is all that stereoisomers of what you've been looking at there, the spatial arrangements determine whether the cis-trans